Okay, hello and welcome back. In this video, we're covering 7.4. It's titled Trigonometric Identities. Um, in other contexts, you might hear these called like verifying identities. Basically, we're going to be using a lot of the trig identities we've seen so far in order to maybe simplify some complex trig expressions and to prove that one trig expression is equal to another one. So let's jump into it. So our first section is on using algebra to simplify some trig expression, meaning we can maybe reduce it or turn it into something that's more simple. Um, the text first defines what they mean by an identity. We've been using this term, a trigonometric identity. Um, they use general function notation here, just basically meaning that two things are equal for all values of x. So we've seen a few identities already. Like our quotient identities, we're saying that the tangent is equal to sine over cosine. And that's true for all values of theta. It's not conditional. So if it was only true for some, like in our last section, we were solving some trig equations that were only true for certain angles. Those would be conditional equations. But something like tangent equals sine over cosine, that's an identity because it's true for all possible angles. It doesn't matter what the angle is, that will always be true. So let's do a quick review of these. We have our quotient identities. Tangent is sine over cosine, and then cotangent is cosine over sine, due to the cotangent being the reciprocal of the tangent. So that's something that we can use. We can utilize that. We also have our reciprocal identities. That's where we defined the cosecant as 1 over sine, the secant is 1 over cosine, and cotangent is 1 over tangent. Again, that's true for all angles, so that makes it an identity. We have our Pythagorean identities. And last time we used this one a lot. Sine squared plus cosine squared equals 1. But there's also two more. And it might be worth just defining where those are coming from. So notice there's this one involving the tangent and the secant. And there's one also involving the cotangent and the cosecant. So we can get those two from the first one if we're starting with, maybe I'll do it up here. If we're starting with sine squared plus cosine squared equals 1. If we divide all of these by cosine squared, if I divide every term by cosine squared, and also on the right side, let's apply some of these other identities. Sine over cosine is tangent, so that would give us the tangent squared. Our second term, cosine squared over cosine squared, that should just cancel, so tangent squared plus 1. And then 1 over cosine is the secant, so 1 over cosine squared would be the secant squared. So we get another Pythagorean identity. That's the one that's shown here. So also useful. And we can solve this, we can say like tangent squared equals secant squared minus 1. We can solve it just for the tangent squared, meaning we can turn a tangent squared into something with the secant. Or as it is now, if we have secant squared, we can express it in terms of the tangent. So that becomes useful. If we go back and let's say instead of dividing by cosine squared, we divide everything by sine squared. So divide this by sine squared, divide this by sine squared. So our first term will become 1. Cosine over sine is the cotangent, so this becomes cotangent squared. And then 1 over sine is the cosecant, so this becomes cosecant squared. And this gives us our second, or I guess our third Pythagorean identity. And they write the cotangent first. So cotangent squared plus 1 equals the cosecant squared. So I would always forget those other two, but you can get them by taking sine squared plus cosine squared equals 1 and either dividing by sine squared or cosine squared. So just wanted to show where those two came from. And then we also have these even odd properties of the sine of really all of the trig functions. So that the sine of negative theta equals negative sine of theta. And remember, that's coming from, let's look at the unit circle. So imagine the sine of negative theta. So imagine some angle theta. Let's imagine like pi over 4. The sine of pi over 4 is root 2 over 2. Well, if we imagine the negative version of that angle, negative pi over 4, the sine of negative pi over 4 is negative root 2 over 2. So the sine of negative theta equals the negative version of the sine of the positive angle. So that's true for any angle for the sine function. Meaning if we have the sine of a negative angle, we can kind of like pull out the negative. The negative can come out in front. And that can be useful sometimes. For the cosine, let's imagine also with pi over 4. This is saying the cosine of negative theta equals the cosine of theta. Let's take pi over 4 for theta as well. The cosine of pi over 4 is positive root 2 over 2. The cosine of negative pi over 4, this still has an x value of root 2 over 2. So they're equal to each other. So that's what this is saying. The cosine of a negative angle is the same as the cosine of the positive angle. So it's coming from like symmetry on the unit circle. So we're calling those even and odd properties, and there's similar ones for the tangent, cosecant, secant, and cotangent. So we can make a similar justification. So with all of these in mind, let's start to apply them to simplify some expressions. So they throw a bunch of these at us here now, and let's go through one by one. So let's look at this first one. It says to simplify the cotangent of theta divided by the cosecant of theta. And it says to simplify this by rewriting each trigonometric function in terms of the sine and cosine functions. So let's try that. Let's turn the cotangent into something with the sine and cosine, and the cosecant into something with the sine or cosine. So cotangent, we said earlier, was defined as the cosine over the sine. So let's just replace that. And cosecant is 1 over the sine. So this looks more messy. It looks like we've made it more complicated. But notice we have a division of two fractions. So when you divide two fractions, you flip the second one and multiply. So let's do that and see how things will reduce. So we have the cosine of theta divided by the sine of theta. This will now be multiplied by sine of theta over 1. So notice here, these signs will cancel and we'll just get the cosine. So this simplifies. So this is a general method for reducing some complicated trig expressions. I'll just describe it generally as convert everything to sines and cosines. Okay, let's look at our second example. It says to show that cosine of theta over 1 plus sine of theta is equal to 1 minus sine of theta over cosine of theta by multiplying the numerator and denominator by 1 minus sine of theta. So this is what they're saying. They're giving us this possible identity. Is this left side equal to the right side? Well, we can take the left side and try to manipulate it until it looks like the right side. So we have the cosine of theta over 1 plus the sine of theta. So they're telling us to multiply both the numerator and the denominator by 1 minus sine of theta. What we're doing is multiplying by the conjugate of this denominator. We have 1 plus sine of theta, we're going to multiply by 1 minus sine of theta. And let's see what this does. So this would give us cosine times 1 minus sine in the numerator. And then in the denominator, we have these two multiplied now. 1 plus the sine of theta times 1 minus the sine of theta. I'm going to leave the numerator as it is now and just focus on the denominator. If I multiply that out, let's imagine foiling this, we would get 1 minus the sine of theta plus the sine of theta minus sine squared of theta. So those middle terms will cancel and I get 1 minus sine of theta, or 1 minus sine squared of theta in the denominator. So that's what I'm going to replace it with. So I'll have cosine times 1 minus sine. Notice it's like a difference of squares in the denominator. 1 minus sine squared of theta. So we just multiplied that denominator out. Now 1 minus sine squared, what can that turn into? And let's keep in mind we're trying to get this expression on the right here. We're trying to produce this. That's part of why I'm not distributing this cosine, because I already have the 1 minus sine. I basically want to ultimately try to cancel that cosine. So 1 minus sine squared of theta. If you remember in our last video, we were playing around with that Pythagorean identity, that sine squared plus cosine squared equals 1. And if I subtract the sine squared over, I get this statement that the cosine squared equals 1 minus sine squared. So notice there's our 1 minus sine squared. So let's use this identity. We can replace 1 minus sine squared with cosine squared. So in my numerator, I still have the cosine of theta times 1 minus sine of theta. And in the denominator, instead of 1 minus sine squared, we can replace that with the cosine squared. And then here, since I have 1 on the top and 2 on the bottom, that cosine squared on the numerator will cancel with one of the cosines in the denominator. And then we'll get that right-hand side of the original expression that we had. 1 minus sine of theta on top over just cosine to the first power on the bottom, because one of them canceled. So we were given this original identity, but we're asking, is it true or not? So we can verify it. This is where the term like verifying an identity comes into play. We can verify it by showing that the left-hand side is equal to the right-hand side via some manipulation using identities or some algebraic techniques. So we can move piece by piece. It's kind of like a little proof. We can make a little change step by step translate something in terms of some other expression until we can reduce things or just turn it into the right side. So the method that we used here was multiplying by the conjugate, in this case the conjugate of the denominator. But then we also used a Pythagorean identity to replace the denominator with cosine squared, and that allowed us to cancel that cosine in the numerator. So a little bit tricky, but we were given that suggestion in the description. It might have been a little bit harder if we were just told to verify this without a little hint there. But that is ultimately what we're working towards. In part C, it asks us, and I'll just write it here, part C asks us to simplify 1 plus the sine of u over the sine of u plus the cotangent of u minus the cosine of u over the cosine of u. And the suggestion they gave us was to rewrite the expression as a single ratio, which means to combine these two fractions together. So that's the strategy we're going to use. So to do that, we need a common denominator. I have sine on the left side, cosine on the right side. So I'm just going to multiply the left fraction by cosine on the top and bottom, and the right fraction by sine on the top and bottom, and then we'll get a common denominator of sine times cosine. So what I mean is on the left fraction, I'll have 1 plus sine of u. That gets multiplied by cosine. And then in the denominator, I'll have sine times cosine. So multiplied by cosine on the top and bottom. And then for my right fraction, I'm going to multiply by sine of u. So this will be multiplied by sine. And then on the denominator, I'll also have sine times cosine. So now I have a common denominator. So let's put it as a single fraction. And it's looking pretty messy, but let's see if things simplify. So we'll have a common denominator of sine u cosine u. In the numerator, this cosine will distribute to both of these terms. So I'll get the cosine of u plus sine times cosine plus, and then here the sine will distribute to both terms. So I would get sine of u times the cotangent of u minus sine of u times cosine. Big messy fraction. All of this is over that common denominator. Make this look a little nicer. All of this is over sine times cosine. Well, let's see. How will this simplify? I see plus sine cosine minus sine cosine, so those two terms will cancel in this big numerator. So we can at least simplify it that much. So I'm going to write this as the cosine of u plus sine times cotangent. Let's turn that cotangent into cosine over sine. Remember, that's how we defined it using a reciprocal identity. Notice here that will allow us to simplify this a little bit. But let's keep it like that for now. We still have our denominator of sine u cosine u. So in our numerator, we can cancel these signs. This will just reduce to cosine plus cosine. So we can write that as 2 cosine u over sine u cosine u. And then notice here, this cosine will cancel with this cosine. So we get 2 over the sine of u. And I think the text stops here, but we could also get rid of this fraction if we see this as 2 times 1 over sine. Well, 1 over sine is the cosecant. We can also express this as 2 times the cosecant of u. So either here or here, it's already really simplified. Remember where we started from up here, this big combination of fractions. What we're saying is ultimately that big messy expression is equal to 2 times the cosecant. So that's like a new identity that we've created. So I kind of like this one because it doesn't have the fraction, but we could also potentially have stopped here if we need to express it just in terms of sine. So this one was a bit longer. So our strategy was to combine fractions, and then we ended up using a quotient identity as well. And then just had to reduce everything. I think there was one more example, part D. Let me write it down here. Part D asks us to simplify. We have sine squared of v minus 1 over the tangent of v times the sine of v minus the tangent of v. And it says to simplify by factoring. That's going to be our strategy. So what can we factor here? I see a couple things. If we look at just the numerator, we have sine squared of v minus 1. So recall the method of difference of squares factoring. If we have two things like a squared minus b squared, recall that this can be factored into a plus b times a minus b. We kind of did that in reverse earlier. When we multiplied something like this out, we got something like that, difference of squares. So that means that that numerator can factor into sine of v plus 1 times sine of v minus 1. And you can multiply that out and see if you get the left-hand side back. So let's do that. That numerator will become sine of v plus 1 times sine of v minus 1. And then in the denominator, we have tangent times sine minus tangent. We can factor a tangent out of that expression. So I can imagine pulling a tangent out times, and what would be left over? We have a sine And then we took that other tangent, so sine of v minus 1. And then notice now we have a sine of v minus 1 on both the top and the bottom. So that whole factor can cancel. So this can reduce to the sine of v plus 1 over the tangent of v. And the text stops here. We could maybe play around with the tangent, convert it into sines and cosines, and see if we can do anything else, but they just want us to practice, seeing this as something that's factorable that allows us to do some cancellation. So we've seen a few different techniques. We've simplified a trig expression by factoring and canceling. We had this longer one where we combined fractions together, used a quotient identity, and canceled. We multiplied by a conjugate of, in this case, of that denominator in order to reduce. And in our first example in part A, we just converted everything to sines and cosines. So let's keep all of these techniques in mind. And in each of these, they gave us these nice hints. But let's see maybe something a little bit more general in part 2. So this has us establish identities, or you could call this verifying identities. So let's go through these and let's think about what we can do. So in example 2, we have the cosecant times the tangent equals the secant. So is this true? You can put a little question mark here. So we saw with the previous example, we can show that this is true by taking one side and then doing some like algebra techniques or using identities in order to show that it's equal to the other side. We want to ultimately turn that left side into the secant. And we could start with either side, but a general rule of thumb is to start with the more complicated side to try to convert it to the simpler side via some kind of reduction. So let's start with that left side. The cosecant times the tangent. We want to turn it into the secant. Well, a general good strategy is to try to just convert everything into sines and cosines and see what reduces. The cosecant is 1 over the sine, and the tangent is sine over cosine. Notice those sines will cancel. We have a sine on top and the bottom. So we're left with 1 over cosine. And 1 over cosine is the reciprocal identity of the secant. And notice that's what we wanted. We wanted to take the left side and convert it to the secant. So at that point, it's like we've just completed a proof. We've shown that the left-hand side is equal to the right-hand side. So that's what they mean by establishing this identity. Just show that one side can be changed into the other side. So what did we do here? We converted to sines and cosines. All right, let's look at example 3. Here we are given sine squared of negative theta plus cosine squared of negative theta equals 1. I mean, it already looks like our Pythagorean identity. We just have some negative thetas in here, but we want to verify this. We want to show that it's true. So what can we do? Well, remember those even and odd identities. We said that the sine of negative theta equals negative sine of theta. We can pull out the negative. And the cosine of negative theta was just equal to the cosine of theta. We can delete the negative for the cosine. We have our trig function squared here, but we can just see this as the sine of negative theta squared plus the cosine of negative theta squared. So we're just looking at the left-hand side. So using this even-odd identity for the sine, we can pull out the negative. So this becomes negative sine of positive theta squared. And for the cosine, we said we can just disregard that negative. It has this property. The cosine of negative theta equals the cosine of theta. Well, if we apply the squared operation, it's going to cancel this negative. Negative sine times negative sine will become positive sine squared. Plus, and then this will give us cosine squared. And we know based on our Pythagorean identity that that's equal to positive 1, which is what we wanted to show. We wanted to show that the left-hand side can be transformed into positive 1. So we've verified, or we've established this identity. So we did a couple things here. We used even and odd properties. And we got the last thing by using the Pythagorean identity. So we did two maneuvers to turn the left side into the right side. All right, let's look at example 4. We want to establish this left-hand side. We have sine squared of negative theta minus cosine squared of negative theta over the sine of negative theta minus the cosine of negative theta. We want to show that that's equal to cosine minus sine of positive theta. So let's take that left side and try to transform it. Let's try to use some identities. Well, what do we have? It looks like in the numerator we have a difference of squares. It looks complicated, but we have something squared minus something else squared. We said that factors into a plus b times a minus b. So let's try that and just see if we can get anything to cancel or simplify. So that should factor into sine of negative theta plus cosine of negative theta times sine of negative theta minus cosine of negative theta. And notice what our denominator is. We have that same second expression, the sine of negative theta minus the cosine of negative theta. So these two whole factors will cancel. So we'll just get that first factor in the numerator, the sine of negative theta plus the cosine of negative theta. Let's use those even and odd properties because ultimately we want some expression just with positive theta instead of negative theta. So we said for the sine, we can pull the negative out in front. So negative sine of theta. And for the cosine of negative theta, that's equal to the cosine of positive theta. And then let's just swap that subtraction around. We can say this will equal cosine of theta minus sine of theta, which is our right-hand side here. So yeah, we're saying this expression is equal to this more complicated one, or that's an identity. So what did we do here? Did a couple of things. We factored using difference of squares. So we factored and simplify. And then we use those even and odd properties again. In order to get rid of the negatives inside of the trig functions. All right, let's look at example 5. We want to establish that 1 plus tangent over 1 plus cotangent equals just the tangent. Can this be true? So let's take the more complicated side, the left side, 1 plus the tangent of u, and then we have 1 plus the cotangent of u on the bottom. So what can we do? Well, I can try to at least get this all expressed in terms of a single trig function. We know that the cotangent is equal to 1 over the tangent. So let's convert that cotangent into 1 over tangent and try to simplify as much as we can. So this will be equal to 1 plus the tangent of u over 1 plus 1 over the tangent of u. So let's try to simplify things a bit more. We can view in that denominator, that's like a 1 over 1. Let's combine those two fractions. We can multiply that 1 by tangent over tangent. So let me write out what I mean. We can express this as 1 plus tangent of u. That 1 we can turn into tangent of u over tangent of u. And then we have 1 plus tangent of u. So I'm getting a common denominator here. So let's combine those together. I'll start working out to the right here. So I have 1 plus tangent of u in the numerator. And then in the denominator, we'll have tangent of u plus 1 over the tangent of u. So still looks pretty messy, but we can view this as a division of two fractions. The numerator is like 1 plus tangent of u over 1. That's this term. And we're dividing by the second fraction, so let's flip it and then multiply. Division of two fractions. This will multiply by the tangent of u would be on top. And then our denominator will be tangent u plus 1, but I can also write that as 1 plus tangent of u. So notice these two are the same. They're going to cancel, and we'll just get the tangent left over. And that's our right-hand side. That's what we're trying to work towards. We wanted to show that this expression is ultimately equal to the tangent of u. You can just transform it using these. It was mostly a lot of algebraic techniques here with the double fractions, but we did use that reciprocal identity. And then the rest was some algebra simplifying these multiple fractions. We could have maybe tried converting everything to sine and cosine. We'd probably end up in the same place too. So there are multiple paths to go through these. Ultimately, this will start to feel like it's kind of like a puzzle game. We're trying to use these rules. We have a certain number of like allowable moves, which are the identities. So we can choose to use them in order to turn one side into the other side. All right, we've got a few more examples. Let's keep going through. So example 6. We have this complicated left side equals to 2 times the cosecant. So let's start with the left side. We have the sine of theta over 1 plus cosine plus 1 plus the cosine over the sine. So it's already in terms of sine and cosine. Let's just try to combine these two fractions together. I want to get a common denominator. So let's multiply the left fraction by sine over sine. That will give us a sine squared in the numerator. And then we'll have sine times 1 plus cosine. And then the right fraction, we want to multiply by 1 plus cosine. We want to multiply by this denominator. So I would get 1 plus cosine times 1 plus cosine. I'm just going to write that as, well, I'll just keep it like that. 1 plus cosine times 1 plus cosine. And then we'll have our common denominator, sine of theta times 1 plus cosine of theta. So let's write this together with our common denominator. So we'll have the sine of theta, and then let's go ahead and multiply that out. Maybe it's worth doing it on the side. We have 1 plus cosine of theta times 1 plus cosine of theta. Let's FOIL that out. So we would get 1 plus cosine plus another cosine, and then the last two terms will give us cosine squared. So we could add these two middle terms together. Let's combine some like terms. So that would give us 1 plus 2 cosine of theta plus cosine squared of theta. Just FOILing that out. Might be worth doing it on the side like that. So let's combine our fractions. We have, it should have been sine squared, plus what we just came up with, plus 1 plus 2 cosine of theta plus cosine squared. And this is all over our common denominator. Sine times 1 plus cosine. So let's keep looking for identities we can apply and what we can reduce. Notice in the numerator we have sine squared plus cosine squared. That's one of our identities. That's our Pythagorean identity. We know that sine squared plus cosine squared equals 1. So that means this would become, you can imagine these are reducing to 1. And then we have plus this other 1. So let's just write that as 2 plus 2 cosine of theta. And we still have our denominator, sine of theta times 1 plus cosine. Notice in the numerator, both terms have a 2, so let's factor that 2 out. So 2 times 1 plus cosine over sine times 1 plus cosine. So we have the same factor on the top and bottom. Those two will cancel. We're left with 2 over sine. And 1 over sine is the cosecant. So 2 times the cosecant of theta, which was our right-hand side of our original expression up here. We wanted to turn this into 2 cosecant, 2 times the cosecant of theta. So what did we do? We combined our fractions together. So we got a common denominator. Combine things together. We used a Pythagorean identity to reduce the numerator. Did a little bit of factoring, and then used a reciprocal identity as our last step. So a lot of tricky maneuvers. Um, and you start to learn these little tricks as you do more and more of these. Um, and at the end of this section, they give us some guidelines, some general strategies. Um, so let's keep going through, and then we'll kind of think about it in general at the end. I think review some general strategies. All right, let's look at example 7. Look at what this is saying. It's saying that the tangent of v plus the cotangent of v over the secant of v times the cosecant, saying that all of this should just be equal to 1. So let's show that that's true. What can we do? Let's just try converting everything to sines and cosines. We know that tangent is sine over cosine. Cotangent is cosine over sine. In our denominator, the secant is 1 over cosine, and the cosecant is 1 over sine. All right, it's looking messy, but let's just try to combine things with these fractions. In the numerator, we need a common denominator. Let's combine those two fractions. So the first one I would multiply by sine. I would want to multiply this first fraction by sine over sine. And then the second fraction I want to multiply by cosine over cosine. That will give us a common denominator. So let's just write that out first. We'd have sine times sine over sine times cosine. I'm putting the sine first, but we could say cosine times sine. The second fraction will become, we're multiplying this one by cosine over cosine, so cosine times cosine over sine times cosine, getting a common denominator. Oh, and I should say that this is being multiplied in this denominator because these were multiplied here. So that will combine a little bit more easily. That'll just give us 1 over cosine times sine, or I can say sine times cosine. So I'm already thinking we're probably going to get that to cancel with these denominators at some point. So let's just continue being careful. Let's combine these together. We can write that as sine squared. This will become cosine squared. And we have a common denominator, so this will become sine squared plus cosine squared over sine times cosine. So that is this numerator here, and it's being divided by this denominator. We have a division of two fractions again. So let's just go ahead and write that as a multiplication. You divide two fractions, you flip the second one, and then multiply. So flipping that denominator, we get sine times cosine over 1. That will cancel nicely. Sine times cosine, sine times cosine. So all we're left with is this sine squared plus cosine squared, and we've seen that is a Pythagorean identity. So this will all just be equal to 1. Sine plus cosine, sine squared plus cosine squared equals positive 1. So this whole thing reduces down to just positive 1. So we did a few things here. Our first step, we just converted to sines and cosines. Then we had to deal with all these messy like double fractions. So we combined fractions in the numerator that ultimately led us here. Got our new denominator. We had a division. This was our new denominator. We had a division of two fractions, so turn that into a multiplication. So that allowed us just to cancel some factors. And then we used a Pythagorean identity here, just to give some labels to these. In the digital homework, it's a little, admittedly, these questions become a little bit awkward because a lot of times they have you go through like step by step and say um, what strategy are you using? Are you applying a Pythagorean identity? Maybe we're converting to sines and cosines or using some algebraic maneuver. So I just want to add these labels in. Okay, I think we get one more example here. We want to show that 1 minus the sine of theta over cosine equals cosine over 1 plus sine. So already keeping in mind, I want to end up with this that involves a 1 plus sine, and I see 1 minus sine here. I think this will be that strategy of multiplying by a conjugate. So let's multiply top and bottom by 1 plus the sine of theta. That'll give us the 1 plus sine on the bottom. So let's just see what this will simplify out to. If we're multiplying those numerators, this will be like a difference of squares again, but let's just multiply it out to show what we have. We have 1 minus sine of theta times 1 plus sine of theta. Well, let's FOIL it out. First two terms will give us a 1. Then we'll get plus 1 sine of theta. Inner terms will give us minus sine of theta, so those will cancel. And then the last two terms, minus sine of theta times positive sine of theta, will give us minus sine squared. So that ends up, those cancel, it reduces to 1 minus sine squared. So that should be our new numerator, 1 minus sine squared theta over cosine times 1 plus sine. So we have that 1 plus sine that we're looking for. It looks like we want to ultimately cancel that cosine and end up with a cosine on top. And I see 1 minus sine squared. Let's remember, we've done this a couple times. If we start with the Pythagorean identity, sine squared plus cosine squared equals 1, and subtract sine squared over, we get this statement, cosine squared equals 1 minus sine squared. So let's replace that 1 minus sine squared in the numerator with cosine squared. Then we have cosine on the bottom times 1 plus sine. And then notice here we'll get that cancellation we want, that cosine will cancel with one of these cosines. And we get our right-hand side. We get the cosine of theta over 1 plus sine of theta, which is our right-hand side. So here we multiplied by the conjugate and then we technically used a Pythagorean identity. and then did some cancellation after that. So another combination of these little tricks. But we've seen a few common themes. So they summarize that up in this little table, guidelines for establishing identities. So let's look at these. It says it's almost always preferable to start with the side containing the more complicated expression. And that's what we've typically been doing. Take the more complicated side and turn it into the more simple side, because we usually want to end up like canceling or doing something like that. It says to rewrite sums or differences of quotients as a single quotient. What they're saying here is like combine fractions. So we did that quite a bit. It says sometimes it helps to rewrite one side in terms of sine and cosine only. So we did that quite a bit. And then they say in general, always keep the goal in mind as you manipulate one side of the expression. Keep in mind the form of the expression on the other side. So we've been doing that too. So just reference back, like, what's our end goal? What are we trying to get to? And that can help you make the next move. So this is good advice. I would also sign off on this. We've been using these strategies as we go through. And so I mentioned this kind of becomes like a puzzle game in a way. We're trying to turn one side, it's like a Rubik's Cube or something. We're trying to transform one particular state into arguably a more simple state. And you have a set of rules. So it's useful to have these like maybe on a sheet of paper ready to reference. These are like a group of identities. These are like legitimate moves that we can make in this game of simplification. We can use these to turn one thing into something else. So we have a set of rules we can use, or identities, and we have to turn some complicated trig statement into something more simple. You can view it that way, and maybe it can be a little bit more fun. All right, so that's it for this section. So we first went through some algebraic skills to simplify trig expressions, and then went through all those examples of establishing an identity. So that'll be all for this video, and I'll see you next time.